talking with people about what I do. And a lot of that is starting the conversation. What is mathematics? What do I actually study? And this slide is written on for longer than it should.
That's a nice question mark.
I think so. So, what is mathematics? Well, one of the problems that we actually have is this slide. One of the problems that we have is that our society tells us that mathematics is this Latin, and presumably as a PhD student, my research is up at the top of this, so nobody else can understand it because I haven't gotten to these other levels. I don't think that's right. And every semester I ask my students, what is mathematics? Where does this ladder actually go? They give me fairly good responses, and they're honest, but they're actually asking me, what do you think mathematics is? And to be honest, I don't really have a good answer to that question. And so what I want to do is kind of fill in this blank and formulate an answer here. And in so doing, I want to give you a couple of examples of theorems and consequences in mathematics that might give you what I call a nerdgasm. So this is Brouwer's fixed-point theorem. This is proved by Hadamard and Brouwer. It's in an area of mathematics known as topology. I'm not going to read the theorem. There's no quiz. This has the consequence that if you take a pint of beer and you chug it, and you have to do it continuously, no gulps, and then your stomach returns the pint of beer to the glass, there will be at least one molecule in that glass that finishes that drink at the same exact location where it started. The second one is this theorem by Dvorak and Coulomb. Coulomb was actually a professor in our department at the University of Colorado. He worked on the Manhattan Project, also developed Monte Carlo algorithms, if you've heard of those. They made this theorem right here, and one of the consequences of this theorem is that there exist two antipodal points on the Earth's surface. Those are points that are opposite through the center of the Earth that share the exact same temperature and barometric pressure at every single instant in time. This is the Harry Ball theorem. This says that if you have a Harry Ball, you cannot comb that Harry Ball without getting a cowlick. Now I should point out that we like to put donuts and balls. Harry Donuts, you can comb Harry Donuts. So Harry Donuts are fine, Harry Balls not fine. And this actually has the consequence that there exists a point on the surface of the Earth at any instant that has a horizontal wind speed of 0. Now, what I actually research is an area called computational group theory. What I do is I take symmetry on steroids and I do it on a computer. And this is great. It's an axiomatic form of mathematics, and I love it. It's something that most people can understand. The theorem that we use is called the orbit stabilizer theorem. This is behind everything that I do. What we do is we take problems and encode them in terms of the axioms of group theory on a computer, and then use the orbit stabilizer theorem to talk about them. For example, one of the things we can do is we can talk about the Rubik's Cube. We can look at the Rubik's Cube as a group, and then we can basically talk about anything interesting about the Rubik's Cube, including solving any random cube in about 100th of a second. Now, this idea was taken last year by some supercomputers and a couple of group theorists, and they proved this theorem just last year that every Rubik's Cube can be solved in at most 20 moves. Now, this is nice, but okay, so we're done with the three-dimensional case. Let's move on. Let's abstract this a bit. This is the four-dimensional Rubik's Cube. This is a four-dimensional cube where each side is a three-dimensional Rubik's Cube. And so we can plug this into a computer. A computer doesn't know the difference between 3D and 4D. And we can ask the computer to solve it too. And so how big is the 4D Rubik's Cube? There are more permutations of the 4D Rubik's Cube than there are atoms in the observable universe. A computer has absolutely no problem dealing with this, by the way. Now, the sad thing is that when I teach mathematics, nobody gets exposed to this stuff that I think is so cool. And nobody discovers these things that I absolutely love. And it strikes me that what we do is we give our students a toolbox that's about 300 to 400 years old. And we tell them that those tools, even though there's some really good stuff in it, those tools are the best tools for solving the problems of today. And I think that's a little bit dishonest. Now, consider this. We live in a time where the number of transistors that are made every single 2 seconds equals the populations of humans on the Earth. I teach those transistors how to do mathematics in a way that no human will ever be capable of. And when I think about it, I think my job is incredibly fun. So that's what mathematics is to me.